says to me, how come so and so, and what happened to it? There we go. I want to just pause this. Let's get into it. And so let's take a look at we're going to refer to our blood pressure spreadsheets. And I wanted to just go back over what was going on there. So we took blood pressure in a sort of unconventional way. Because we had the leaky cuff, huh? And well, first thing we did though, yeah, right. And so we made these time and pressure graphs. And then we saw this characteristic shape, and we actually knew about the characteristic shape. So we have this characteristic shape. And we actually observed it. But our pressure sensor is the pressure sensor range is less than the difference, the delta of the systolic and diastolic. And our range was like, what was it? 10 millimeters of mercury, I think. And of course, the range here is like, can be, let's say 140 over 30. Yeah, so that's like, can be like the range here can be 100 or more. So we decided we needed to do a kind of trigger on the shape to identify the systolic and the diastolic. Oops, that was in the place I wanted it to be. In fact, we can gain a little bit here. Let's put this here, but we'll shrink it a little bit because I want to leave a little room. Oh, okay. So then, let's see, this is our, the delta here is about 100 millimeters. So we have, let's see, trigger on the shape. So we had to decide let's think about it. Right. And to help us, we decided to do a background subtraction. And the background, remember, is basically the decaying pressure. So the PT graph of the leaky sensor. Leaky cuff. Because that is going to be, this is going to be our sort of, not exactly, but it's going to be sort of our mean pressure, which you see up here. So that way we can focus on just the shapes. And then we had to decide on trigger points. Where is the systolic and where is the diastolic? Okay, so just yell if you need me to go back. Just trying to, all right. So we realized, no, at least no easy physical fit function. And what that means is that, like, if for an example is y equals mx plus b, excuse me, then if this was a distance equals to speed times the time plus starting distance that is a physical fit function. The things that we fit for, the slope and the y-intercept, represent physical quantities. But since we have no need, to extrapolate, meaning we don't need to predict anything. So with this equation, I could tell you in the future time, I could tell you the distance. So not only for the time of the graph, I could say, well, if the graph goes from 0 to 10 seconds, I can tell you what the position is at 20 seconds. Excuse me. So then we decided to do an interpolation, which is simply stay within the data range. It means more than that, but it's good enough for us, and it's true. And we decided to do a polynomial fit. To get the background. And as a subheading to that, we did some data qualities management. I can't remember the technique. And basically that was, we made sure that the data only was the decaying pressure. So there was the pump up, and then at the end, like I had to click a button, or maybe there was some other disturbance going on. But we made sure we took the data, we chopped off the beginning and the end, and then we used the trend line for seed numbers. And also not only seed numbers. Hold on a minute on that one. We used, oops, come on. The trend line gets us two things, actually. Come on. The trend line determines the what order, polynomial, and it tells us, gives us the seed numbers. As always, yell at me if you need me to go back. And so how do we decide what order? Well, the trend line will give us 0, 1, 2, 3, 4, etc. And just so let's first of all, what is a polynomial? So there's a sub 0, x to the 0 power, plus a sub 1, x to the 1 power, plus a sub 2, x squared, plus, and then plus a sub n, x to the n power. And so whatever, an n order polynomial. And and like 90% of the time, I don't know, most of the time, the A's are not physical. So if we try to extrapolate, we try to go to beyond the data, it's like major fail. So it's only really good to give you, in the science world, we do this to try to help us. Like if we just can't think of a fit function, we'll do a polynomial fit to help give us some idea of what's going on. And of course, for us, don't forget x is t time for the blood pressure. So in the trend line settings, we went 0, 1, 2, 3, 4, and you examine the highest order coefficient, A, highest, and compare to the next highest. And so when A sub n is much greater than A sub n minus 1, then we stop. Although, and in fact, what we do is, let's be careful. Give me a minute. Don't hate me. Right. What we do, is that if we go from order n to order m, so if A sub n is much greater than A sub n minus 1, A sub m minus 1, if the right. So you have A sub n minus A sub n minus 1 and A sub m minus if the two of these are about equal, then we stay with this one. And I hope I didn't make that more confusing. But we can look at the spreadsheet, and then you can write it up with your own words if that is super confusing. I'll get ready over here, and then I'll bring it back. On Monday, I just wrote in actual numbers for M and N, but I'm trying to generalize it. Okay. Okay, so let's take a look at this. So there's our trend line. Come on. Where is it? Trend line. There it is. Okay. So we look at the coefficients here, huh? So we're at the third order fit, and okay, that's, well, what's that? 3,000 times difference. That one is 10,000 times difference. So I like that. But now I go to fifth order, and there's not a lot different. Not a lot of difference there. In fact, I don't know, maybe we could have gone with the fifth order. But for sure, there is very little difference between the first two coefficients. There's only one order of magnitude difference, even between the first three. And then this one, there's only one order of magnitude. Whereas in this one, there's two orders of magnitude. So that's why we stopped here. Going up to the fifth order polynomial didn't make much difference. Oh, in fact, I suppose the original criteria is true then. Oh my gosh, forgive me. Ha, isn't that stupid? When I'm too low, this is not a big enough difference. And when I'm too high, it's not a big enough difference. So I was right the first time. Oh my God. See, blonde roots go into the brain, they say. Okay. So basically, without being too confusing, if I'm too low n, a sub n will not be that much bigger than a n minus 1, and even if I'm too high of an n. So we find the one that's just the Goldilocks. We need the Goldilocks n. There's that blonde hair again. Okay. Now, seed numbers. Why do we need seed numbers? In fact, let's duplicate this first so that I'll get rid of some stuff here. So remember, I think I've described this to you. When we set up the residual squared, each parameter, I can plot the parameter value, like the slope, and the value of the residual squared, and it has a minima. And it also is the shape of a parabola. Hopefully you remember y equals x squared. That's a parabola. At least it is when you're close to the true value. It's almost, you can mathematically prove it. And in fact, a single parameter fit or a simple two parameter linear fit, they're always parabolas, it turns out, but in general they may not be. So I'm going to go to the next slide, but everything is there still, except this added stuff. So what can happen is, when you have a lot of parameters, if you get too far away from the central value, there may be another point like this that resembles the correct one. So it's sort of a stability point, a teacup. Like you throw a marble into a teacup or a bowl. Excuse me. But in a like we're having 5 parameters. A fourth order polynomial is 5 parameters. There's a chance that the solver, or even us personally, will find a minimum, but it won't be the real minimum, the absolute minimum. And if you know anything about baseball, we call it stepping into a bucket. When you're a batter, steps out, swings the bat, but steps sideways. And the solver can get stuck there. So if we give it the seed values will be pretty close to the actual values. So it's not exactly a limit. If this fit hadn't worked out for us, I avoided this topic because we didn't need it, but just so you know why give you a better idea of why we need seed values. The primary reason is the one I just gave you. The second reason, so first of all, this one is a simple one. We want to make sure that they are allowed to go negative. Now let's say that we're suspicious of this fit. So let's say we have this number 1. We can add limits. So we can say that parameter 1 has to be greater than or equal to negative 31, or maybe negative 32. And it also has to be less than or equal to negative 28, for example. And there's our two constraints. So that is a rigid limit that we can put on it. But generally speaking, the seed value should put us close to the within the part of the fit, the residual square that's actually a parabola and is actually the minimum. And it worked in our case. Delete. What did that do? Oh, I have to pick one. I just want to get rid of the... Oh, I see. Right? And delete. We didn't need them. Okay. All right. And then we went to our graph, and then we plotted. We got our not yet, not residuals. We got our seed values, And we just copied them. There may be a way of extracting these. I don't remember, or I don't know. So we just simply wrote them down. We typed them in. So we put the seed values. Into a table. And that was 0, 1, 2, 3, 4. In fact, we did it the other way around. And we had them. Then we made a fit equation. And let's just call it, oh, I'm worried about that. These are not Excel references. So it's a sub 4, a sub 3. I'll put it small just. And so then we made a fit line equation, and which is going to be a4 times t to the 4th plus a3 t to the 3rd, etc. Then we made the residuals column. We made the residuals squared. And then we added the sum of the residuals squared. And then we used solver to refine the polynomial coefficients. What time is it? Okay, been an hour. And then we plotted the residuals. And remember, that's data minus the fit. And the fit is the background. So this is, it ultimately is background subtracted data. And then we decided on the trigger points. And then we added horizontal and vertical lines to the graph to show systolic and diastolic. These are the horizontals. And then calculate pulse rate. And those are the vertical lines. Sure. No worries. Just you let me know. This is our in the spreadsheet. You're welcome. All right, so before I forget, here are the, I think I gave you this last time, but these are the, you have these tabs down below. And, right, I have to double check if there's Jenny 01 and Jenny. I don't remember. Which one is the right one now? He was a good boy, and I've been really working hard to keep my own logbook up to speed. So that's Jenny. Jenny 01. I have another one, but I don't want you to work. No, wait a minute. Well, we can figure it out. Jenny or Jenny 01? No, that's Jenny. Okay, so not Jenny 01. And this one should be Dr. H. Oh, this should be Dr. H02. What am I doing? Huh? I mean, I'm looking at the tabs down. See the very bottom of my screen here? With this, I see Dr. H01, Jenny 01, Jenny, Dr. H02. So this one up here should be Dr. H02. The guys in the Monday class probably hate me now. Okay. And I believe, but I don't want you to analyze all of these, just 2 or 3 of them. Let's see. Let's just write it down to be correct. Jenny 01 is 140. See, I have my notebook is not comprehensible to me a week later. See that? Or 2 weeks later. Not all of it. And I wish somebody had kicked my butt at an early age and forced me to keep a good notebook. Okay. There we go. So just get that written down so we don't forget. Oh yeah, 63-year-old male, 56-year-old female, and Christian is 28. Because the manual asks you if this is normal for this person or that person. And let me just take a quick look here. What's this? Oh, we just already... right. All right, we'll go over this. Okay, all right, let's not delete that. Okay. Let's just yell if you want me to bring this back. Let's take a look here. Now, one thing I was thinking one could add into here. So in principle, I made a video for you guys, or we went over in class last week. So is everybody down with being able to put these lines on here? Is everybody able to put the lines on? Does anybody need me to go over it? Okay, I'm not hearing anything. And I showed you in the video, I showed how, or during class, I showed you how to zoom in and change things. This is my legend. It's always a good thing to have. This one could use a white background so I could can see it better. Oops, I don't want that. I don't want it to be white. There we go. Yeah, there's various ways you can play with this. Okay, so anyways, I had an idea that maybe we put more horizontal lines, because first of all, I wanted to have a way to show the actual value and the ones I decided on. So how hard would it be to do this again? Let's see. So what would I do? I would do this, copy, and insert. Okay. And I just create a blank one there. So this is systolic. Right. So we put this one as no, it's this, the y-axis. So this is systolic actual. And this is diastolic actual. Well, anyways, I better just stick to what we're doing here. And I'm thinking of ways to improve it. So let's take a look. So we had decided, I think, when we looked at the residuals for the diastolic was to see where it was no longer able to track the lowest pressure. And you remember I had this rubber here, and what happens is that when you're near the diastolic, your blood vessel still closes, and then as the average the pressure in the cuff goes below that, then at this point the pressure measurement, it doesn't go as low anymore. So when the amount of swing of the blood, that's right, the amount of swing of the blood vessel isn't as much. So it's not, this is something we thought about on Monday. It's not only the negative part. I think you have to look at somehow there's a way to, and we're not going to do this. This is just what I'm going to do for the future, but just to give you an idea of my thought processes. I think that what you do is there's a way to set up to calculate this delta here for each of these. And in the beginning, it's small because now the blood vessel is spending most of its time closed. And then, excuse me, and then also the range, the time that it's open is actually smaller than the 10 millimeter range of the pressure sensor, which in fact you can see isn't even that much. Look at the y-axis. The pressure sensor basically can only do 2 or 3. That's it. Wow. But at some point, then it's opening and closing at the end, but the range of motion is still bigger than the 10 millimeters. But now when it stops closing, Yeah, I got to think. So I think that it's when this distance here starts to shrink. We had decided the low point was here, if you remember, because this is where from this pulse to that one it changed. But my feeling is that it's something like this. So anyways, the point is now we decide on a criteria. So if I use my new criteria, I might decide that it's here. And then I have to find out where that is on the main graph, because with the background subtraction, I don't know the actual pressure here. So here's a cool feature. I can put the, let's move that a little bit. I can put my cursor here, and you see how 18.46 appears? That's the time coordinate there. So then I can go here and I can type in 18.46, and then my time cursor moves, and then I can zoom in on that area, which looks like I want, let's say 15 to 20. Yeah, and if I wanted to, I could also zoom in here, which is going to be 100 to 150. Right, so now I say this is what I'm going to call my low pressure. So then that's my diastolic, so I can start bringing that down. So it looks like 102, whoops, oh, a little bit lower than that, 101. So now I have my diastolic. Now, the actual value, see, this is why it might be useful to have 4 horizontal lines. I'm not requiring you to do that. So remember, the actual is 111. And that is, oh, look at that. That could be, look at how flat that is right there. Okay, so this is at when? It's not telling me. 16.8 seconds. So let's take a look at here. 16.04. Oh, here it is. So that's interesting. So I actually think that 16.04 might actually represent the actual value. But look, this is not about getting the right and wrong answer, right, guys? We defined the spot. We decided on a trigger point, and it's defensible. When I explain this to people, they will say, oh, yeah, I think that's okay. Now, one thing you notice here, this is a little wavy, and probably a fifth order polynomial would have been better. But again, that's beyond the scope. So let's try this. So I said maybe, come on, 16.02, more like 16 seconds. Let's take a look. 16. And that would have put the pressure here, 113. So, of course, you know, it's not perfect no matter what. And this is 109. So this little kink here is interesting. I wonder if that little extra shape there, and again, this is beyond today. See it right there. I got to do some thinking about that one. Cool. So anyways, we decide on a trigger point, and you can find it here. This is 20.9, and maybe this one. So we decided it's this one, 19.3. And this just helps us to find it. Oh, what happened? Maybe we decided something else, huh? All right, 18.5. So anyway, you guys, you guys are to decide this. I'm just giving you some ideas, and you maybe you already have, right? So that's beautiful. Look at that. So then I just bring this down again. This is 102 or 101, right? And there we go. Now now we want to zoom back out, and this was easy. Axis options, reset, and then axis options, reset, and then where do we say it started? So we can zoom in here, and this was yeah, maybe we chopped too much off, so we're going to say this point is the, but we can also go backwards, and we decided, I think, this one, and that is, come on, tell me what one. 9.6 seconds. So let's go 9.6. Look at that. And did I type in the actual number? So we got the actual number of the systolic pretty good, huh? Did it pretty well. Not pretty good. All right. So anyways, those are we decided on trigger points, and then how do you get the pulse? We went over that, and I have this thing set up to tell me I have to put my 2 time marks on peaks. And so we pick a place where we have some nice, well-defined peaks. And then I'm going to say, it looks like 12. I'm going to get moving here. We're taking too much time. 12 to 18. Right. And then we put this at 100 to... what is it? 150. Oops, went off the graph. So it's because I hit 120. And my leg. Oh, great! Look at that. So what's that? 13.7. We can get close. And then the next one is 14.58. So 14.58. And then the trick is to get them to the exact, you have to decide which is the exact spot that they repeat. And what is the BPM here? 68. And the actual was 72. In fact, this one here could move up a little bit. Let's say 13.75. And look at that, 72.2. All right. Boy, we're spending way too much. Well, you know what? I'm not going to have a report for this due next week. And I'll have the final notebook be due, but we'll do a summary like this next week, but it'll be quicker. And then of the electrocardiograph, and then we'll do the whatever the next lab is. Okay, because that I think will take a longish time. All right. Yeah. Taking too much time on this. Are there any questions? Yeah. This is new stuff, right, Felicidad? And I just hit on it too. It's no one's ever done this like this before. I've gotten every semester closer and closer. So I'm not, you know, I'm making up expectations as I go, and remember, I reward hard work. You don't have to get everything correct. Yeah, and that's another thing that the pandemic is doing. I'm making lots of great videos. Okay, so first of all, I want to stop this one because it's the blood pressure.